So Edinburgh is very special to me because I did my PhD here. I mean, in the other building, the JCMB as it was called. And yeah, I wanted maybe to compare. So I started my PhD in 1989, which is an important year for Berlin because after I left, they took the wall down 6 weeks later, right? So it's clearly related to my move. So I wanted to compare what happened in 1989 and not the wall plus later, because so in this year I first learned about type theory, and I learned by using Randy Pollock's Lego system. Yeah, it's fun to do constructions. That's the line when you started it. And I want to, and I believe I've learned something, maybe, and I want to compare it how I'm doing things now. So in 1989, when we thought about type theory, we thought about untyped terms, yeah, with variables, with named variables, yeah. So that the named variables was something I very early decided is not a good idea, and I quickly converted to theorem. But I stuck to these untyped terms. So let's put this in bracket. And then we had small step reduction on untyped terms, small step reduction, which then gives rise to an equivalence relation. And oh yeah, and another thing to define this small step reduction, I had defined one place substitution. So substitute one term for one variable. And when you start to do this, you discover that you also need weakening. And in my PhD, I formalized the proof of strong normalization for system F. And I had to prove lots of theorems about substitution and weakening. And I proved them by just starting to prove what I needed, and then others showed up. And it could never make any, I mean, it wasn't very systematic, but it worked. Oh yeah, and then what about semantics? Semantics versus syntax. So that was a real issue. So there was a real mismatch between the syntax, which was untyped, and the typing rules. Or maybe I should have said something about this untyped terms and typing rules, right? Typing relation. So this relation was defined. And there was a bit of a mismatch between the semantics and the syntax, and you had to prove theorems like Thomas Streicher famously proved this initiality theorem, which basically says that the syntax of type theory with these rules give rise to an initial model of type theory in the categorical sense. So this was the real achievement, and people are still working on this initiality theorems, not me. So that means that's how I do things different. So I decided that we need only type terms. So I never want to talk about, I mean, at some point, people always tell me, when connecting to the real world, you may have to live with people not always typing typed terms, which is fair enough. But when I define my type theory, I don't want to, I'm really about type terms. So I want to only define type terms. And there should be type de Bruijn terms, whatever I mean by this. So, okay. And what about equality? So yeah, so here in the old days, we had to have a special rule, the conversion rule. We had a rule like if A has type A and A is convertible to B, then gamma A has type B. Right? This was this famous conversion rule. But now I think I like to view this equality as equality. So define equality of terms, to type terms to be beta eta. And why does this make sense? So okay, so I'm thinking and I'm working, I'm living in type theory and influenced by homotopy type theory. But the real insight to me is that if I define a type, I should also define the equality of this type. So defining a type means not just defining the elements, but also define the elements of the equality. And in Hot you can repeat this because you can talk then about the equality of the equality and so on. But that's an important idea that the propositional equality of a type is associated with the type, or it should be. If you want to define a type, it's not enough to define the elements. You also need to define what the equality type is. Doing this, I think it's important because it gives us a sort of more extensional and more mathematical theory, which is more mentionable. And okay, maybe I should have done this before. So one-place substitution, I do parallel substitution. How do I write parallel? Like this? Or the other way around? I never know. That's parallel substitution. So I'm not, for me, life is much easier when I define parallel substitution. So also substitution is morphisms between contexts. And then one-place substitution is just a special case. It's derived from this. And syntax is just the initial semantics. So there is, and maybe in a way you could almost say what I'm saying now is sort of in a way boring or obvious because I'm just defining the syntax. So that's the initial semantics, and there's nothing to do. There's no initiality theorem to be proven. It is built in.
Thorsten, this idea of defining equality to be beta eta, that might require some computation.
No. 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 I just define. I mean, equalities are not always decidable, right?
All right, deciding the equality might.
Yeah, it's defined, you know.
Oh, you're in.
Yeah. Okay.
Another question.
Yes.
Does it mean that equality is going to be somehow the same between different types or different kinds, or can it vary?
The equality is defined between type terms, right? So it's always specific to the context and the type. So maybe it becomes clearer in a moment. But yeah. That's very good. I appreciate it. I find it much easier if people ask questions. If I talk here, stay and talk, it doesn't make much sense. So let me just sort of try to invent type theory. I mean, I could just write some terms of category theory and say, take the initial of those categories with families, and that's it, end of story. But let me construct it. So if we have type theory, what's the first ingredient? The first ingredient is the set of context, right? So I'm here, I'm using ACTA syntax. I could even write data in front of it, but I don't. So I define a set of contexts. So contexts are the assumptions of the types of the variables. And what's next? So next I have types. Types are in a context. So it's a family. It's con to set. It's a dependent type. For every context, I have the type of types in this context. And then what comes next? I have terms. So a term given a context given a type in this context, I define the set of terms. I think, I hope. And what's missing is substitutions. So depending on what's the day of the week, I give them different names. Today it's Tuesday, so I call them Tunes. So they're given two contexts, so they're parallel substitutions between contexts. So this is my signature, and I'm now going to inductively define constructors for these types. And this is the first thing where we need maybe a recent, recent development of type theory to be able to do something like this, to be able to define. Oh, I think somebody wrote a PhD on these sort of things, and we need what we call inductive types. So what are inductive types? Exactly this sort of situation where we define some types and some other types which depend on those types, but we define them all mutual. And so usually you think the mutual definition of type should be reducible to non-mutual definition. But that's not the case if they depend on each other, because then you cannot tear them apart. So
this is because you're doing full type theory rather than say just simply type lambda calculus.
Right. Yes. In simply type lambda calculus, yeah, exactly, because you do dependent types. Right? So dependent types, are what we want to do, and also we just look today at system F, where you don't need this dependency. But there's lots of repetition, I find, because you have something going for types and kinds, and then for terms and types. And this is easier in a type theory because you just add another universe, and so you avoid this repetition. But you have to live with this mutuality, And this is actually something I'm still looking at and try to understand. I mean, you can do this in ACTA, and you can't. I mean, you can write down these sort of types in ACTA, but then ACTA wants you to define all the constructors together, and that's not what you want to do. You want to define some constructors and then some other constructors depending on them. In particular, if we go on and define equality, so I'm not just defining the elements, I'm also going to define the equality. And equality are constructors. They are constructors for the equality type, which makes perfect sense what I said before, that to every type we associate equality. So when we define inductive type, we inductively not just define the elements, we also inductively define the equality. And that's what we call, and these are called actually quotient inductive types, or short QIITs or QIITs. I don't know. And they're a special case of heats, but so quotient inductive types, to understand them is still something I like to do. I mean, we have now a reduction for certain families of quotient inductive types to just basic inductive types or W types. So that's actually quite nice. Okay. So let me just start. I mean, I'm not going to define all of type theory. How many hours do I have? Okay, that's not good. So let's just start. So how do we define context? That should be quite easy. It's an empty context, all right? And then I can even write this as rules, all right? I can write the constructors as rules. This was epigram style, yeah. Epigram was a dependent type language with a two-dimensional syntax, yeah, implemented in Emacs, yeah, you know who, Conor McBride. So what else do we have? So if we have a context gamma, and I have an A in type of gamma, I can form a new context, the gamma.A, and you see, okay, I certainly don't want to use names here, but I can just extend them. Okay. So yes. so now I want to define substitutions. So I want to define rules for substitutions. And the first one, I mean, the terms, right? So let me just, as I say, I just do some examples. So what is, we have an empty substitution, yeah, which is which goes from any context gamma to the empty context, yeah. So it's like you think of substitutions like something like a substitution from gamma to delta, where delta is x0 in a0 to xn in an, is a sequence of the substitution here is a sequence of a0, which is a term in gamma of a0, and a1, which is a term always in gamma, but in a1, where x0 is substituted with a0, right? And so on. So an an is a term in gamma where an, and here we have got all the substitution x0, a0, and so on. Right? So that's the intuition. So obviously, if delta is empty, then I just have the empty sequence, right? But if gamma is not empty, then what is my rule? So I have a substitution, let's call it delta, terms gamma delta, and now I want to extend my delta, yeah? So delta has a type in delta. But I have a term, A is a term, and it should be a term in gamma. We have seen in this example dot explanation that all the terms are in gamma, right? But now A is in delta, so that doesn't fit. But it makes sense because I have all these substitution. So A should be, you should apply substitution delta here, right? So that means we need a new constructor, but let me first of all what I mean. So delta comma A is then a substitution from gamma to delta dot A. But now I need this operation here. Well, let me do this also epigram. Why do I stop using epigram now? This iPad can do epigram, it seems, yeah. So let me do this as a rule, because what is it if I have a type in context gamma, and then this is important. Now I have a gamma, which is a substitution from delta to gamma, right? So what it does, it gives you terms for all the variables in gamma which live in delta, right? And so that is why substitution for me is always contravariant. So we have this now type delta. Okay, makes sense. But now when we define substitution for types, types contain terms. So we also need substitution for terms, right? And let me just copy these assumptions there. And add some other assumptions, so that A is a term in context gamma of type A, and the gamma is the same as up there. Then I have, what happened now? How do I get rid of this? Oh, like this. Okay. Then I also have another substitution. So actually, when working in Acta, I do have to just, I can't overload. No, okay. Why cannot I overload it? That's actually a good question. Yes, I stopped explaining how I actually hack this into Acta, because if you hack it into Acta, well, let me get to back later. There's this problem that you have to define all the constructors together, no? And I didn't give the answer what you do in this case. But let me just first ignore this. So A gamma is a term in delta of A. The substitution is applied. If you look at this example, hopefully it makes sense. Okay, So I cannot overload these. Okay, why I cannot overload these constructors in ACTA? I can actually overload constructors, but it turns out to overcome the technical restriction that I cannot order my constructors in any order I like. I have to go do a trick which was observed or invented by Shumi, who was a PhD student. Who was not a PhD student, was a master student of Ambrus Kaposi in Budapest, and he observed something which seems to be like a hack, but actually turns out also theoretically interesting, namely that you can just define this by defining a sort of microscopic universe, and then so you define just this family inductively, and then you say there is a little con in U, and for example there is a little tie which is EL con to U. So you inductively not just define the elements of the types, you also define the types themselves as inductive constructors for U, and then you define constructors for EL of this type at the same time. And now you can just say big con is EL of little con, right? And tie of gamma is EL of little tie of gamma. Right? So this trick, which this technique, means that when we define inductive types, we only need this special case. Right? And also, when we do this in ACTA, we can order the constructors for this type in any order we like. Right? So it's both a hack to implement something in ACTA, but it's also a nice theoretical observation, because when we study inductive types, we do not have to think about arbitrary signatures. It's enough to think about this one. Does that make sense? Okay, so now let me. Okay, so oh yes, I defined this important rules for extending context. Now you can also invert it. So you have this rule, and you have the rule which goes up, right? Which I call also, depending on the day, that's pi 0 and pi 1. So if you have a substitution gamma comma a, you want to go back the components, right? And okay, how do I do this now? Yes, I wasn't very clever what I did. But using these pi 0 and pi 1, I can now implement my de Bruijn variables, right? So it gives rise to the variables, because, for example, to define, okay, let me do some experiment whether I manage to copy this rule here. Yeah, copy. Yeah. Ooh, what happened now? Okay, that was not very clever to even try this. Why is it not doing paste? Ah, there. Ah, here we are. Okay, that's what I wanted. Okay, so because what I want is the variable 0 should have what should it be? If I have a variable, the last variable a, I want to have a term of type a, but it's not a, it's a weekend, right? So a weekend, whatever this is a substitution, which is actually pi 1 of it, if you think about it. Oh, identity. Have I introduced it? Okay, so I have to define also the identity substitution. So if we have gamma is in con, then I have it which is the substitution terms from gamma to gamma. And there are some equations for this. So, so if I want to define this, then what is it? And you can figure out it's actually 0. I want to have a term from the identity of delta dot A. So you use the identity in or gamma dot A. Yeah, so gamma dot A to gamma dot A, and then I do the second projection of pi1, pi2. Okay. So this is then second projection pi2 of gamma A. And similar, we can implement the De Bruijn, the type De Bruijn successor, right? Which is if I have a term, let's say M of term of gamma A, I want to have what I call suck of M. So you may say this should only work for variables, but it works for terms. It's of weakening, which is let's say gamma dot B. So A and B are in context gamma, and A is then again pi1 of it. And what is suck of M? Suck of M is yeah, it's M with pi1 of it. So okay, so what I'm saying here, this setup, let me then recover the usual syntax or the usual De Bruijn syntax. And but as I sort of indicated, I need quite a lot of equations, right? I need already yes, I need equations for ID, I need equations for substitution, and so on. So for example, I would like something like if I have I haven't introduced any types. Yeah, let me just yeah. So okay, so actually we have here substitution, but we may also want to have a substitution for substitutions, right? I may substitute in a substitution, right? So here I have a substitution for types, that's a substitution for terms. What is substitution for substitution? How can I substitute in a substitution? So what is the rule here? So if I have a substitution from gamma to delta, but now, what do I call this? It's called delta. And now I have the substitution gamma, which goes from, and now I need a new Greek letter. That's always tricky. Does anybody know another Greek letter? I'm running out of Greek letter. Theta? I mean, theta is cool, no? Gamma. Then I substitute all the gammas here by doing my term substitution, and I get something in theta to delta. But the question is, how do I call it? I've seen this sort of thing before. I mean, I could call it delta bracket gamma, no? But maybe that's not the most fashionable name, right? Because people in Edinburgh certainly have seen some category theory and they know that that should be circle, right? Okay. Okay. Yeah. So it's composition. Yeah, even if you never heard about category theory, you would invent this, right? Substitution of substitutions, which is always my slogan. My slogan about category theory: you can either learn it or reinvent it. Okay, so let me now step a bit back and say, actually, what's going on here? The rules, there can be instead of presenting this way, which actually follows the way I sort of discovered them, instead of, I mean, I reinvented category theory, but that sometimes the best way to learn something is to reinvent it, right? And so what's happening? So con together with substitution, they form a category, right? And maybe I'll call this category called C. And what are the types? Now, you may not be very surprised to learn that there are some laws about the type and the substitution. We have tie, right? And we have this operation applying a substitution for a type. That looks like, can anybody say the F word? Well, this is a tricky term in Edinburgh. Yeah, it's the F word. It's a functor, right? Or actually a presheaf, right? We are a bit sophisticated. It's a presheaf. It's a functor. So in C op to set, right? It really has the right direction. It's opposite C op. This is what we want. Aha. And this gives us all the laws. So instead of when I wrote my PhD, sort of like discovering the laws by sort of trying them, you sort of know what the laws are, and all works out nicely, right? And what is Tim? Tim is also, and there is a substitution operation here, right, for terms, which should have a different name, really. So I call these big T and this little t or something, yeah. But is it, I think this is a functor? It's a bit of a funny functor, actually. There is a word for this in category theory. It's a functor over the elements of another functor. It's a presheaf over the elements of type. And I'm not going to write down what is the category of elements, but this sort of thing is what you could also call a dependent functor. If you don't want to learn the category of elements, then the presheaf over the category of elements is a dependent functor. And it's actually easy to see what's happening if you think about it, because we had this dependency already in this rule. So now we have, for example, we have a rule that A of it is equal to A. And we want to say, so let's call this, so this I call A it, and it's a constructor for this equality. Okay. But now we want to say that A it is equal to A, but the two things are in different types, right? So we need a heterogeneous equality, so A it, which uses the previous equality, right? It's really an equality, it's a heterogeneous equality, a path over a path, as it's called. And this picture here, the same is true for composition, really is a type theoretic way to understand the situation that we have a functor over the elements of another functor. It's really a dependent functor. Okay, so that's and all these conditions here are inductive, can be viewed as an inductive definition because they're all strictly positive. And we can understand this as an inductive definition of an inductive type, actually as a quotient inductive type, because we're not just giving constructors for the elements, but also constructors for equalities. And so this is, I present this as an inductive definition, but we can also replace data by record, right? And build a structure of these things. Yeah, instead of defining inductively, we can define a structure. And then it is a well-known thing, it's called categories with families. Which is just correct. And so the situation is that my syntax is, by definition, the initial category with families. Yeah. Okay, let's have a quick look at pi types. So, I mean, in the moment, actually, I'm just defining the empty type in a very sophisticated way because it puts something in. I mean, one way to put something in is to say, okay, I have a family and I insert this family. So I have like a family of types and elements, which I could call the universe, and then introduce this universe into this type theory, so that I have something to start with. But we also want to have closure under type constructors. So that's a famous example, the pi type. So how does this work? If I have an A as a type in gamma, and B is a type in gamma extended by A, then I have pi AB, which is a type in gamma. Right? And then how do I get beta and eta laws? Actually, it's very easy. So it's if I have a term gamma dot A and B, I also get one from gamma to pi AB. Okay, and this one I call lambda, and then I just invert it and call it up. And the beta and eta law are just that this is the morphism, right? Which again, strictly positive equations, and don't have to compute them. I can just state them. And okay, this is not the application as you know and love, right? But what I'm saying is you can derive the usual definition of application from this one. But we need some more rules. So for example, you need that this is the natural isomorphism, and you need also substitution rule for pi. I mean, you need something like pi AB, and now substituted gamma should be the same as pi A gamma and B. And now you have to define this operation extending a substitution. So the dot is functorial. But here I also need an equation, a naturality equation. This is the Beck-Chevalier condition. But here I need a lambda, let's put M, I don't know, today. Gamma is the same as lambda M gamma dot A, and you need only one, because if you've done your category theory, you know that for natural isomorphism, you only have to say that one of them is natural, the other naturality you get for free. So that's nice, but it's still there's lots of noise, right? Because everything I define will be natural, and all the constructors I define should be functorial. So I'm really spending far too much boilerplate. And maybe the question is, can I get rid of this boilerplate? Yeah, and I can.
So
maybe
earlier, Thorsten, you were sort of talking about this is a very concrete thing that you were encoding in AGDA.
Yeah.
And now you've drawn this natural isomorphism.
Yes, which is just a shorthand for some AGDA terms, right? Yeah, it's okay. So what I have is
I see. You define
up compass lambda is the identity. Okay, these are okay. They are triple equalities, and this isomorphism just means that lambda composed with up equals to the identity, and the other way out as well.
Does AGDA know that, or do you tell AGDA?
I tell AGDA. This is the constructor. There's a constructor, but let me write it down. Beta, which says, let me see. If I do up after lambda, or maybe I could even do not point. I mean, like this. Lambda of M, just right, is M, is this beta or is this eta? Now I'm getting confused. This is beta, right? So this is an equation, this is a constructor for this equality. Yeah, so it doesn't compute it, it just knows that this is the equality between terms. Right? Eta is the other one. Yeah. So, okay, so we can compute it, so we can actually, and we did this. So if you want to compute decide the equality turns out this equality is decidable. And how do you do this? By computing normal forms. And how do you compute normal forms? Yeah, and how do you normalize? Expecting something normal. Yeah, so this is normalization by aberration. We construct a free sheaf model where the neutral terms live in a category of weakenings actually, and from this we get can compute the normal forms.
You can do that for type theory.
Yes, yes, we have a paper about this. Yeah, that was a new thing because yeah, I mean. That's what we did. So this is joint work with Ambrus Kaposi. So first we wrote a paper where we showed how to define type theory, and then we put a paper where we showed how we normalize the types. Okay, there's two things I want to say. How much time do I have?
You have 10 minutes, including questions, so maybe round up in 5 minutes.
Okay, I may not have enough time to explain this, but so one thing is you want to get rid of this boilerplate. So actually, I want to define my type theory in a different way. I want to use higher order abstract syntax, right? Yeah, and I want to say, forget about these stupid contexts. I mean, there's just everywhere. You have to write gammas everywhere. So when you write them everywhere, you may as well forget them. Yeah. So I define type is an element in some universe, U, whatever. Yeah. And term is simply indexed by types. And I forget all these stupid gammas which go everywhere. Yeah. And then I want to say, for example, that the term, so pi, now what is pi? Pi is if you have a type and you have a function from terms of this type to u, yeah, no, to tie, sorry, to tie, then I get a type, right? Yeah, I get all these gammas are there's no carpet here. No, yeah. I need a bit of a carpet. I will explain the carpet in a second, okay? And then you want this beta and eta equation is much easier. It's that terms of pi a b are the same as, well, but I don't need to talk about naturality. Everything is natural, right? So a in term of a to term of b of a, right? That's what I would like to write, and I can. So how do I connect this with what I said before? Now, yeah, it turns out it's actually very easy. All I need to know is that there is a model of type theory, which is the pre-sheaf model. And I can take pre-sheaves over the syntax. And in this pre-sheaf model, the U is the Hoffmann-Streicher universe, an element in the universe is just the same in the meaning of type is really a pre-sheaf. C is my copy to set. And the meaning of terms, it turns out, it requires a bit of translation, is actually this beast. This is in my model. So contexts are interpreted in the semantics as pre-sheafs. They are C or C op to set. So what I'm doing is I move myself into this pre-sheaf model of the syntax, and then I can use higher order abstract syntax. Now, yeah, I need one time. I do need to do my rule construction of a model, but after this, all I say, and there may be, I need only pi types and the universe. All I say, I can say in this language and get rid of the boilerplate of substitution and naturality, because everything is natural by definition. Everything is functorial because I cannot say anything else. Yeah, it's newspeak. You cannot say anything evil. Yeah, you can only say things which are functorial and natural. If you want naturality, I mean, this is always a goal of religion. You want the things to be natural, so you get this here for free. Yeah? Okay, that's one of the things I wanted to say. The other thing I wanted to say, I will only very shortly say, if you really believe in homotopy type theory, which I hope everybody does, what else would you believe in type theory? I mean, it's sick. So if you really believe in homotopy type theory, we have a problem, Houston. Why? Because I have to, and there's one constructor I didn't mention. If I just type this into hot and say this is a higher inductive type, then I'm lacking some equations. Yes, because it's not the thing I want. I want actually, I want a type with a decidable equality. And there's a theorem in homotopy type theory that a type with decidable equality has to be what's called an H set, has to be a type with equality with a proposition in the sense of type theory. It's at most one element, UIP boards, whatever. Yeah? And that means I have to add a constructor here to force things to be sets. Yeah, I have one constructor like is set for context. Yeah, if I have two contexts, gamma and delta are context. Now, so we are back in the previous world, and I have two proofs, P and Q, that gamma. This is a space here. delta, then I want that P is equal to Q. Yeah. So this forces my context to be set, and actually I need my types to be set. That's the real thing. But this is the problem. If I now want to define a model, I want to define a CWF. Yeah? So I want to interpret my syntax in a model. Then the problem is that the most natural model is the model of sets, the CWF of sets. Yeah. And here the interpretation of con is set. And set is not a set. Yeah. But this is not to do with size. Size is easy to deal with. It's not a set because equality of set is isomorphism. What else would it be? And isomorphism is not unique. There's more than one isomorphism between two types. So here we have a problem, right? And yes, so if anybody asks me a question, then I can tell you ways of how to deal with this problem. Yes. Yeah.
I have a question.
Yeah.
You should repeat my question. How do you deal with that problem?
So the question of Phil Wadler is, how do I deal with this problem? Okay, so I have to prove a coherence theorem. So what I do, I define actually, okay, I could go omega level up, but I go only one level up. So I define what is called coherent type theory. So I give constructors one level up and cut off one level higher. So why is this important? Because what I get now is the category of context is actually a category in the sense of what? What's a category? A category has a one type of objects and home sets. Yeah? And this category of set is a category in this sense. So but now I can prove, or I believe I can prove, oh, it's a conjecture. It's an unfinished proof, but I think I know more or less how to do it. So what I can then show that the initial coherence is a coherent type theory. So coherent type theory, so con is not a set. Con is a one type or a groupoid, right? And tie goes from con to groupoid. Yeah? Whereas terms and substitutions are still sets. So here I need extra equalities. I need equalities one level up, equalities for two categories, basically, or two CWFs. But it turns out, or it's conjecture, that the initial coherent type theory turns out to be set based. So even though I allow this extra freedom, when I construct the initial one, I get sets because there's nothing which induces a non-trivial equality in this theory. Which means I get this coherence theorem sort of for free. I can work in my set-based syntax and then use this fact that the coherent type theory, the initial one is a set, to eliminate into something which is not a set, but it's a groupoid. And this way I can actually interpret my syntax in the CWF, the set CWF, which is a 2 CWF. Does this make sense? So that's a proof theorem which I haven't written up, and there's some technical details. This technical details is horrible, like especially if you use a proof checker. Yes, these proof checkers are very difficult to intimidate. You know. That's my answer. Are there any more questions? Yeah.
Thank you. A question. Have you looked at context with more structure? So as soon as we have well-typed syntax, we like to write program transformations of programs. And sometimes it's really convenient to know that some variables do not depend on others, for instance. So a context that could be some kind of DAG instead of just a linear telescope. We tell this like automatic.
No, I haven't looked at this, but one thing would be to define this as sort of superstructure on the context. Does that make sense? You could have a family of context that contains this information. So this way you could leave the context as they are, but you have this superstructure on top of it. But I actually would be also interesting to do this for this quantitative type theory and other variations.
I have questions about this notion of HOAS you have here.
Yeah.
So is that the same in some sense or a generalization of what we normally understand by higher order abstract syntax?
Yes.
Because I thought normal encoding. Oh, I guess. For instance, if we encode higher order abstract syntax, we often the strong version is in predicate. Is this weak HOAS or strong HOAS?
So you should repeat the question
Also,
briefly.
the question was whether, when we input HOAS, whether we need impredicativity. I don't think so, but we need to deal with size here. I mean, the pre-sheaf model sort of was set, and even if we ignore the question of coherence, it's a large model. But there should be no impredicativity. We just have to make, I think so. We just have to make sure that we don't confuse the level.
So is the impredicativity we get just an artifact of trying to encode HOAS in a stupid way?
Yeah, I suspect, but okay, I'm quite careful. But I mean, for this construction, as far as I know, we don't need impredicativity.
And then what about another issue with HOAS is, can you convert between this representation and the first order representation?
Yes.
And even prove that those versions
Yes.
are correct in type theory itself?
Yes.
Because
You can repeat the.
Okay. The question was whether what was the question? Whether we can convert back and forth between the higher order abstract syntax and the type theories as well, right? And yes, so that's the case. So can convert between the pre-sheaf model and the first order syntax.
Right, that's interesting, because again, with this sort of strong HOAS encoding, well, that key has a proof that you can't, well, no, proof of correctness of a translation, but you can't do that proof without internalizing parametricity. So you can't kind of prove it inside a type theory.
I mean, what we get here is because we have naturality. So naturality should be enough parametricity you need, but happy to look at this in more detail. This is, by the way, it's based on, I mean, the observation that you can understand HOAS via pre-sheaves is due to Martin Hoffman. But this one has been used also by a number of people, also in Budapest. So I think it's pretty reasonable. There's a little thing you have to say when if you define these things here, you need one thing. You need a little star here, okay? And from the star, you get this context extension. So the context extension operation, you cannot encode in the HOAS. You need to say that the terms can use context extension. And this corresponds to saying that you have a universe of locally representable pre-sheaves. So, and you can, so having a locally representable pre-sheaf means basically context extension. So this is a little detail you have to add at this point. And you can also, if you add more families like this, then you have different kinds of variables, basically. So you can vary what sort of context you have got. And I think these things are called SOGAs. Second order generalized algebraic theories. Okay.
I have a question here from James Wood.
Uh-huh.
So I'll read it to you and then you should repeat it for the audience. How much time should the working type theorist be spending with the QIIT you've presented, as opposed to with CWFs or whatever other axiomatization of the category of models they want?
How much, so the question was, how much time should we spend on QIITs and CWFs. So I suspect the question was, should the working type theoretician know about this view, or was it? Yeah. I think, as I said before, these sort of abstractions which come from category theory, there's, as far as I see, two options. You can either learn them or reinvent them. So I mean, I find they show up quite natural if you think of how to structure your presentation of types theory in a satisfying way. But obviously, this is a matter of taste, you know. So I can approve that this is good taste. I think it is good taste, and I think to me it avoids to go into many dark alleys, getting confused. Having a little bit of structure, having a bit of guidance, helps me to structure my work and to avoid having to prove weird things, which I, yeah. So I would say, yeah, that should be the way, in my view, that should be the way to think about types theory.
You think about the CWFs and not about the QIITs.
No, both. I mean, the QIIT is just the initial CWF, so there's no difference, right? I mean, so okay. Yeah, so CWF and this QIIT representation, as I said, I could have done this whole talk in 5 minutes, saying the initial category with a pre-sheaf and a representable pre-sheaf over the elements is what I mean by the syntax of types theory. But I thought I give a bit of a sort of stepwise.
So there's a follow-up question. Does the QIIT do any more than witness the existence of the unique initial model?
That's what it does.
No.
Yeah, that's what it does. Yeah. I mean, okay, so here is, so there are people, some of my colleagues, who are very interested in proving some sort of initiality theorems. And I always say, well, why would you do this? Because we do have the means with higher inductive types or higher inductive types, which we need anyway, to define the initial model just by writing down the rules, right? There's nothing, there's no ingenuity required. So okay, and then you can say, yes, but at some point you want to relate your abstract syntax to concrete syntax. And I say, yes, that needs to be done. And obviously you want to have type checkers, you want to use equality conversion checkers, and so on. But this should not be part of the definition of type theory, right? This is the same as if you think about this to be on the right level of abstraction. So if you think about it, has anybody ever proved that beta reduction preserves matching brackets? Yeah. It's a stupid question, right? Because we think of terms as trees, yeah. So to think, I mean, this is always the problem I have with students, yeah. They like to think of terms as strings, and then they do string manipulation to do something on terms. Don't, right? Manipulate trees. But this course of getting better continues, you know. I say only think about type terms and only think about type terms with the right equality, right? Or actually think of them only in this pre-shift category, and so you achieve the appropriate level of abstraction to talk about the things you want to talk about.